So let's start with better activation functions. So before I get into activation functions, right, let me first tell you why I care about activation functions. Why do I actually want to come up with better activation functions? So I'll start with the following question. What makes deep neural networks powerful? Among other things, what is this one thing which makes it powerful? So let me give you this intuition. I have a deep network, okay, and don't worry, it's a thin network, but I could have had a wide network also, but just for illustration, I have taken a thin network. Now imagine that each of these neurons that you have, if I replace the sigmoid in each layer by a simple linear transformation. Hey, by the way, this is technically incorrect. So orange is always input, so there should not be a sigmoid there, right? Either add one more layer there or let's change the figure, okay? Fine. So suppose I replace all these sigmoids by linear transformations. What would y be? Can you write y as a function of x? What would it be? Give me the function. It will just be this, right? So first you will do w1 of x, which is this guy. Then you'll take w2 of that, then w3 of that, and w4 of that, right? So I could actually have written this just as y equal to wx, where w is equal to w4, w3, w2, w1. So there is no depth here. There is actually only one weight which I could have learned. You get that? Right? If you just have all linear transformations, then essentially you don't have so many weights. You just have one weight throughout. Does that make sense? So what you're learning eventually is just y as a linear function of x. And initially at some point we started off with such linear functions, right? W transpose x in the case of perceptron and MP neurons. So what does that lead to? What kind of decision boundaries does that lead to? Linear decision boundaries, right? So if you don't have these non-linearities, we cannot have these arbitrary decision boundaries. We'll only be left with linear decision boundaries. In particular, we'll not be able to solve this problem that we had, right? So we were given some red and blue points, and there was no way to draw a line such that the red points are separated from the blue points. What we needed is some kind of circles or ellipses to separate the red points from the blue points. That cannot be done with linear decision boundaries. That can happen only if you use a deep neural network with non-linear decision boundaries. And we actually have a proof for that. What's that proof? The universal approximation theorem actually told us, right? So that's why non-linearities or the activation functions play a very important role in the success of deep neural networks, right? Hence, we want to examine them very closely and see what are the newer kinds of non-linearities that have been proposed. So we'll always start with the basics. So we'll start with sigmoid, see what are the problems with sigmoid, and then see what we can do to solve some of these problems, okay? So this is what the sigmoid function looks like. You have seen it a million times. And it actually constrains the input to 0 to 1, right? So it takes some input and it constrains it to values between 0 to 1. Now, since we are always interested in gradients, right? Because the entire training, and that's why I did that precursor in the first module, the training always depends on gradient. So it's always important to look at what does the gradient look like. So we know what the gradient looks like. We have computed this. It's just sigmoid of x into 1 minus sigmoid of x, okay? So now let us see what happens if we use such a sigmoid neuron in a deep neural network, right? This is a deep neural network, and without loss of generality, I'm going to use a thin deep network, but the same holds for a wide deep network also. So suppose you are interested in computing the gradient with respect to W2, right? At some point in the chain rule, you will have this term. How many of you are convinced about this? Okay. And that will lead to this. Could that cause a problem? So at one of the terms in your chain rule is going to be this dou h3 by dou a3. I'm assuming all of you are convinced about that. And I've given you the exact formula for dou h3 by dou a3. Will that lead to a problem? Good. So what is the consequence of this? To answer this, we need to understand the concept of saturation, right? So a sigmoid neuron is said to have saturated if its output is 1 or 0, or rather close to 1 or close to 0, okay? What would happen in that case to the gradient? It will vanish, right? Because sigmoid of x into 1 minus sigmoid of x, so at either extremes it's going to vanish, and you don't even need the formula for that. You can just see it from the diagram, right? Because the gradient here is going to be 0. That's obvious, right? It's just a horizontal line. So this gradient would be 0. So fine, why does it bother us? What is our entire training premise based on? Gradients, right? What is our update rule? What happens if this guy is 0? No update. The weights just stay where they are, right? That means the training gets stalled, right? So think about this, right? If all the neurons in your network have saturated, that means all the weights, the gradients will be 0. That means all the weights will remain where they are. You pass another input, nothing is going to change, right? It will still be 0. So if the neurons have saturated, your training will just stall, okay? So that was one of the reasons which used to cause problem in training deep neural networks earlier, right? So that's one of the reasons why it was not converging, because these weights used to, these neurons used to saturate. So this is one problem with sigmoid neurons. A saturated sigmoid neuron can cause the gradient to vanish, okay? But why would the neurons saturate, right? I mean, what would cause them to saturate? Okay, if they saturate, fine, the gradients will vanish, but why would they saturate? You should be able to get some hints from the figure that has been drawn. So this is actually, that x needs to be changed. So on the x-axis we have x, quite obviously, but that has to be something else, okay? So what is happening is, what does the sigmoid neuron do? It takes this aggregated, oh, someone just disappeared, okay, I didn't, okay. So is it very boring today? No, right, okay. So you have this aggregated sum of the inputs. Once you have that aggregation, you apply the sigmoid. Now tell me, when would it saturate? When the aggregation is very large. That means one of the two things could happen. Either the x's are very large or the w's are very large. Would the x's be large? I see a lot of you saying no. Why? Good. We normalize them, right? We make sure they are between 0 to 1. So we don't allow those arbitrary large values of pressure, density and so on, right? We make sure they are between 0 to 1. So then the weights can be a problem, right? Now why would the weights be large? Move later. First, if I initialize the weights to a large value, if I initialize all my weights in my infinite wisdom to a large value, what would happen? Right from the first training example itself, wi xi would take on a very large value and your neurons will start saturating, right? So imagine if all the weights throughout my network are initialized to large values, then right from training instance 0, my neurons will start saturating and I will not be able to train anything. How many of you experienced this while doing backpropagation? And the others did not do the assignment, they copied it. Please raise your hands, how many of you experienced it? Now many more hands will be raised. Still no? Okay, honest people. Yeah, that's a paradox, but yeah. Consider what would happen if you use sigmoid neurons and initialize the weights to a very high value. They'll start saturating and hence you will have this problem of vanishing gradients, okay? Everyone gets this? So this is a problem with the sigmoid neurons. The other problem with sigmoid neurons, which is very interesting, is that they are not zero-centered. What do I mean by that? They're not zero-centered, that's what I mean. Okay, so sigmoids are not zero-centered. What do I mean with that? Mean by that? They're not zero-centered. The value is between 0 to 1, right? So the average cannot be 0. It's always going to be above 0. Okay, sigmoid neurons are always going to take on positive values between 0 to 1. So why is that a problem? So that's an interesting explanation. Oh, did I say that, did I put the acknowledgements somewhere? So all of this material that I've been talking about, it's taken from Andre Karpathy's lecture notes. So here's this interesting explanation for this. So now consider this particular network, okay? And I'm going to focus only on this part. That means the output layer and just the layer before that. And the layer before that has these two weights, W1 and W2. I'm going to focus on that. Okay. So to update these weights, I need to compute what? I'll carry a gun from next time. Oh, all this is on camera, okay? So what do we need to compute? Gradients. Okay, now you'll answer. So we need to compute the gradient with respect to W1 and W2, and this is what it's going to look like. What is the red part and blue part? Why red and blue? The red part is dash for both, common for both, right? Okay. So this is going to be common. I don't know why I did that. Okay. just okay. Yeah, good. Okay. So this red part is common for both. And what's the blue part actually? What is dou A3 by dou W1? H21 and dou A3 by dou W2. Everyone gets this? You're reading this formula and telling me, right? So dou A3 by dou W1 is just H21 and dou A3 by dou W2 is just H22. Okay, so let me just plug in those values. And note that H21 and H22 are between 0 to 1. So can you make some interesting commentary on this? Interesting but useful, not just philosophical stuff. These two derivatives are for the weights at a given layer. I've just taken two weights, but I could have taken n weights and the same thing would have hold, right? Because I know that the derivative is proportional to the input that it gets, and the rest of the part is going to be constant because that's coming from the chain rule up to the previous layer, right? So now what is happening because of that? Just to make fun of you guys, how many of you get that? Sorry, okay, good, good. Yeah, it's not very straightforward, but let's see. So if the first common term in red is positive, right, then what would happen to these two guys? They would both be positive, right, because H21 and H22 are positive. Now if the first common term in red is negative, then what would happen to these two guys? Both negative. So that means the gradients of the weights at a particular layer will either all be positive or they'll all be negative. You get that? That's because of this common part and the blue part. The blue part we know is positive, so what matters is the common part, and that common part can either be positive or negative for all of them together, right? That means for a given layer, all the gradients at a layer are either positive or they are all negative. So let's see what's the implication of that, right? So this actually restricts the possible update directions. So which is the quadrant which has all positive? First, okay, sorry for embarrassing you, yeah. And all the negative is the third quadrant. That means your movements can only happen in the first quadrant and the third quadrant. So do you see a problem with this? Right? So you're going to actually try to move that your theta, which is a collection of W1 and W2, is theta minus eta into the gradient, right? And you know that this vector, which is the gradient vector, can either be positive, that means it can lie in the first quadrant, or it can lie in the third quadrant. These movements are not possible. That means there are certain turns or certain movements or certain directions that I am not allowed to take. So what would this mean? It would take a dash time to converge. Longer time to converge, right? Because I am restricting my movement. So imagine you have to go from destination to destination B, and I say that you can never take a right turn, right? And there's going to be some problem, right? It will take longer to reach there. Unless the direction is to the left, right? Unless your destination is to the left. But that will not happen, okay? So suppose this is the optimal W star. And we start with some random initialization because that's where we are going to start. Then the only way I can reach it is by making a series of these kind of movements, right? A zigzag pattern is what I'll have to take because these are the only movements which are allowed. Or some movements which are allowed, and it will lead to a certain cryptic pattern, and it will not be able to have the complete freedom of moving in the direction which would have directly taken me to the optimal. How many of you get this argument? Okay, good. So that's a problem with something not being zero centered. Okay. And lastly, sigmoids are expensive to compute because you have to do this EXP. Right? It's not something as easier as something else that we'll see in the lecture today. Okay. So these are some problems with sigmoid functions. So now people, yeah. So okay, so this is some issues that were there with sigmoid functions. So this pointed that okay, maybe we should try better activation functions. That's why TANH became very popular. But TANH is not something which happened post 2006. Right? This was like 92, 93 when I think Jan LeCun had started moving to TANH from sigmoid functions. Right? Now again here all your inputs are compressed between -1 to 1. Okay, your inputs are now zero centered, which takes care of this problem which I mentioned at the end, right? That these directions of movements are constrained, okay? And what is the derivative of this function? 1 minus tan h square, right? What happens at saturation, even without looking at the formula? The gradient would vanish to 0, right? So the vanishing gradient problem is still there. What you have solved is the problem of zero centering, right? And that itself used to give better results than just using a sigmoid function. But it's still computationally expensive because you still have to do these e raised to components, right? you still have to compute these exponential powers, right? So it's still computationally expensive. So then in around 2012, I guess, is when this Relu was introduced in the context of convolutional neural networks, right? And this is what the Relu function actually looks like. Is this a non-linear function? It just looks like a line, right? Why is it a non-linear function? It is a non-linear function, right? Because x is, you cannot write x, the output as a function of, as a linear transformation of x, you have this 0. In fact, if you take two Relu functions smartly, you can actually get the sigmoid, you can get an approximate for the sigmoid function. So you can go back and check this, right? So if you take these two functions and subtract one from the other, what is this? This is a Relu function. This is also a Relu function, right? So I define Relu as max of 0, x. So both of these are Relu functions, some variant of that. And now if you subtract one from the other, you will actually get a approximation of the sigmoid function, right? And this cannot happen if you have two linear functions. Take any two linear functions, you will not be able to get this kind of an approximation, okay? So Relu is a non-linear function. What are the advantages of Relu? One is it does not saturate in the positive region, right? It's computationally very efficient. The output is either 0 or x. There's no powers, nothing like that, right? And in practice, it converges much faster than sigmoid and tanh. So that's what this 2012 paper showed. And now Relu has actually become more or less the standard in all convolutional neural networks, okay? But there is still a caveat while using Relu, okay? So the derivative of Relu, we can see that if x is less than 0, then the derivative is going to be 0, right? And if x is greater than 0, then the derivative is going to be 1. And that straight away follows from the definition of Relu, which is 0 or x. So when it's 0, the derivative will be 0, and when it's x, the derivative will be 1. So now consider this given network, and let us assume, and this is not a very far-fetched assumption, it can happen in practice, that at some point, a large gradient causes the bias B to be updated to a large negative value, okay? So what I'm saying is that something happens, and B gets updated to a large negative value, okay? Now what would happen to this quantity? Remember, this quantity which I have circled is actually the input to the blue colored Relu neuron that I have. So I'm asking you what would happen to that input. That input would become negative. So the neuron would output 0, and I'm calling it a dead neuron. Why? If the input is 0, the input is negative, then the Relu function's output would be 0. What would happen to the gradients during backpropagation? 0. That means what would happen to the weights? Won't be updated, right? Now, but that's fine, right? If you give some other input, this will recover. Why am I calling it dead? Means permanent, right? Unless you are in some fantasy world, but dead is dead, right? So why am I saying that it's dead? I would give it a next input, and then probably things would be okay. Bias is still very negative because nothing is getting updated, right? Your bias is still very negative. You know that x1 and x2 are constrained because you have normalized them, right? And w1 and w2 have not been updated. So still the situation does not change. So what happens is that once a Relu neuron dies, because somewhere in the chain rule you got a 0, it will stay dead forever, okay? It will never be able to come out of that. It will always produce a negative output. That means that output will be clamped to 0. That means no gradients will flow back, and that means all the weights will not get updated connected to that neuron, right? So in practice, when you train a network with Relu, you will observe that a large fraction of the units can die if the learning rate is set too high. Why this if condition? What was the assumption that I made? That the bias receives a large negative update. And that is possible if your learning rate is very high, because you got some small negative gradient, but your learning rate blew it up, okay? Now what's the practical implication of this? If you're training a network and a large number of your Relu neurons have died, what does it mean? Most parts of your network are dash. Useless. They're not learning any feature, nothing, right? It's all 0. That means you have these large number of parameters which are just getting wasted because they feed into a Relu function and the Relu function just keeps outputting 0. So if you have n neurons in a particular layer and most of them are 0, that means you are not really learning an n-dimensional feature representation, you are just learning a much smaller feature representation, right? So can you give me a simple way of, one simple way of avoiding this among many other ways? No, dropout is statistical, right? It's probabilistic. This is like always dead. One thing is to update the weight to a positive value. And 0.01, mind you, is a large positive value. Right? Later on we'll see why. But 0.01 is reasonably large. Okay? So we're going to initialize the weight bias to a positive value so that even if this large negative gradient flows through, there's still a chance that it will not become very negative and hence it will not mess up the things the way it does. That's one solution to that, right? But still you will find that even after that, the Relu neuron, a lot of those can die, but still in practice they work better for a deep convolutional neural network, okay? And we can also use other variants of Relu. So there have been, to avoid this dead neuron problem, there are other variants of Relu which have been proposed and that's what we look at next, okay? So there's something known as a Leaky Relu. Is it obvious from the equation what it does, right? So instead of producing 0, it will just produce a very small value proportional to the input. Now what would happen to the gradients? They will not saturate, right? You will have, the gradient would be, if the input is negative, what would the gradient be? 0.01, right? So that means some gradient will still flow through. How many of you get this? Right? So that means if you use a leaky Relu neuron, some gradient would still flow through. So just understand this trend, right? That, and this is, I mean, all this stuff is simple. There's nothing great in this. But just put it in context, right? So in 2006 to 2009, people realized, okay, now we can train networks and maybe whatever we have done with unsupervised pre-training actually corresponds to better initializations or better optimizations or better activations and so on. So now let's try doing research in that. So that led to the discovery of Relu. Now people started observing problems with Relu and then proposed a variant of it, which is Leaky Relu, right? So that's how this area has now become very prolific and grown, right? So we started off with this seed idea that it is possible to train these deep neural networks, and now we are trying to arrive at better and better ways of doing it, making it more and more easier to train them and take care of some of these irregularities which existed earlier. So one of them being sigmoid not being a very neat function to optimize with, right? So that's what all this is about. Individually, all of these are probably easy for you to understand. And once you go back and look at the slides, there's nothing great in this. But what I want you to really understand is this bigger picture of what is happening, right? As long as you get that, I'm fine with it. Okay? And of course, Leaky Relu is again computationally very efficient. There's no exponents, no squares, nothing like that. And it's close to zero-centered, right? It's still not zero-centered, but close to zero-centered because you have outputs on both sides. Okay? And then someone came up with a generalization of this, which is parametric Relu. So why 0.01? Make it alpha x. And alpha will also be a parameter. It's a trainable parameter. It's not a hyperparameter. Okay? How many of you know the difference between parameter and hyperparameter? Okay, you have used this in the backpropagation assignment, right? So it's a trainable hyperparameter. It will get optimized along with your other parameters in the network. Okay? So then someone said, okay, Leaky Relu fine, parametric Relu fine. Let's try to do exponential Relu. Okay? So it has all the benefits of Relu. It ensures that at least a small gradient will flow through even when your inputs are negative. That means it avoids this dead neuron problem. Again, close to zero-centered outputs, but it's expensive because now we have added this exponential, right? So these are all ideas which came out during this period and all of them were shown to work better than the other and so on. And of course, at the end, I'll have to tell you a final conclusion, right? Whenever I give you so many possibilities, so I've given you sigmoid, tanh, Relu, parametric, leaky, exponential. Now what do you use, right? The idea is not to confuse you, but to give you one solution which would largely work. Yeah. What regularization? Yeah, you could have done that. Yeah. That's another. So there's exactly. So a lot of this research, right, which has happened in this period, it's not. A lot of it is heuristic, right? You saw one problem with Relu. Okay, the neurons are saturated. Okay, just make it something which does not saturate, right? So that's there. It's possible that the other solutions would also work. There's not that this is the only solution which works. Okay. Now then, someone came out with max out neuron, which is a generalization of Relu and Leaky Relu. Why do I say it's a generalization? What was Relu? That means W1 equal to B1 equal to 0, W2 equal to 1. So it's a special case of the max out neuron. What about Leaky Relu? This was parametric Relu, but again, what about, so now what is happening? W1 equal to alpha, B1 equal to 0, W2 equal to 1, B2 equal to 0. So you see how it generalizes, right? So this is how these variants kept coming up, okay? Now the problem of course is doubles the number of parameters, right? Because you earlier had only W transpose X plus B. Now you have W1 transpose B1, W2 transpose B2 and so on, right? So that's actually doubling the number of parameters that you had. So now coming to the final conclusion of all of this, right? So what you need to remember is that sigmoids are bad. So no one uses sigmoids in convolutional neural networks. They're still used somewhere. I'm sorry about this. Relu is more or less the standard unit for convolutional neural networks. So any standard CNN that you will pick up, it will use Relu as the activation function. If you want, you can explore Leaky Relu, max out, Elu and so on. But it will require a lot of careful tuning. So if you want to use something out of the box, Relu is just fine. Relu just works fine in practice despite all this dead neuron and other problems. Yeah, so then the argument for that is that how often will you reach the point x equal to 0, right? So the chance of that happening is very, very low. And if you get there, you can always approximate it by some epsilon or something. And for that training instance, just go on, right? But anyways, you are making so many approximations with stochastic and mini batch and so on. So this is one more approximation. Right? So that's how people typically deal with it. But in most cases, it will not, I mean, that point appearing is very low, right? But the question is valid. And tanh sigmoids are still used in LSTMs and RNNs, which we'll see at some later point in the course, okay? So there are a couple of more modules that I need to do. So we'll just take a break here.